Hello everyone. In this lesson, we will discuss optimization. Learning objective: to set up and solve optimization problems in several applied fields. Exploration: a manufacturer wants you to construct an open-top box with a square base, a surface area of 108 square inches, and with maximum volume. A. Write a formula for the base area of the box. Use x for the side length. Answer: base area equals x squared. B. Write a formula for the volume of the box. Use h for the height. Answer: v is equal to x squared times h. Recall the volume of a box is length times width times height, or base area times height. Where your base area was x squared and your given height here is h, where your variable for your height is h, so then v will be equal to x times h, that's x squared times h. C. Write a formula for the total surface area of the box. Then set this equal to 108. Surface area is equal to 4xh plus x squared. Now this x squared represents the area of the base of the box, and this 4xh exists because for the four sides around the box, the area will be x times h, and there are four of these. The top is opened, so we do not have an area at the top. This surface area is equal to 108, so we set the 4xh plus x squared equals 108. D. Solve the above formula for h in terms of x. So this, we will just do a bit of algebra here. Subtract x squared from both sides first. So we'd have 4xh would be equal to 108 minus x squared, and then we divide both sides by 4x, and we end up with h is equal to 108 minus x squared over 4x. Part E. Substitute the result into the volume formula to get volume in terms of x only. So when we plug this 108 minus x squared over 4x for h in the volume formula, we have x squared times quantity 108 minus x squared over 4x, and if we distribute this x squared through and divide by the 4x, we're going to end up with 27x minus x cubed over 4. F. How do we use this result to find the maximum volume? Well, first of all, you want to find a feasible domain, and then afterwards you want to set the derivative of v with respect to x equal to 0, and then solve for x. Okay? So that is how you would use the result to find the maximum volume. So let's do it. A possible domain, then for x, we want x to be a positive number, so we set x greater than or equal to 0. And we also know that the surface area, total surface area, will be 108. So then if we had set h equal to 0, then we could make this base area equal all of the surface area, and that means that the maximum that x could be will be the square root of 108, because then if we make our x squared equals 108, then x would be at most the square root of 108. That's the most x can be. So if we take the derivative, then we take the derivative dv dx, or we want to call that v prime of x for notation's sake, that's fine, will be equal to 27 minus 3x squared over 4 by our power rule. Set that equal to 0, and then solve for x, so 3x squared over 4 equals 27. 3x squared will be equal to 108, so x will be equal to plus or minus 6. But we know within our feasible domain that x cannot be negative. So we choose x to be equal to 6 because that is in our feasible domain. And then we want to solve for h. So plug this x back into equation for h, which had an x in it. So h should be equal to 108 minus 6 squared over 4 times 6. So h should be equal to 3. So the maximum volume that we can have in terms of our dimensions, which were 6 by 6 by 3, would be 108 inches cubed. Let's look at our steps that we use to solve the optimization problem. In general, what you want to do first of all is to draw a picture, if possible, and label all variables. Step 2, determine which quantity is to be maximized or minimized and for what range of the value of the other variables. 3, write a formula for the quantity to be maximized or minimized in terms of the other variables. This formula may involve more than one variable. 4, write any equations relating to the independent variables in the formula for step 3. Use equations to write the quantity to be maximized or minimized as a function of one variable. 5, identify the domain of consideration for the function in step 4 based on the physical problem to be solved. 6, locate the maximum or minimum value of the function in step 4. This step usually involves looking for critical points or evaluating a function at the endpoints. Now let us look at another problem. A rectangular garden is to be constructed using a rock wall as one side of the garden and a wire fencing for the other 3 sides. There is a 100 feet of wire fencing to be used in the construction. A, determine the dimensions that will create a garden of maximum area. B, what is the maximum area? Begin this problem by drawing a picture to try to get to a solution. So here's our wall, some little green thing on it, maybe moss or something like that. There's a wall. There's no fencing on this side with the wall. However, there's fencing on 3 sides. The 2 sides perpendicular to the wall, we label those sides X, and the side parallel to the wall, we label it Y. There's 100 feet of fencing. The variables therefore are X, which is the fence perpendicular to the wall, Y, the fence parallel to the wall, A, the area of the garden. We'll also set up a P for your perimeter of the fence. Now P will be equal to 2x plus y because the 2 sides labeled x and a side labeled y, and P will be for your length of your fence. Plug it in 100 for P. We have 100 is equal to 2x plus y. This is our constraint. We're limited by the amount of fencing that we have. What is the area formula? Area is equal to x times y. So then we want to express this area in terms of one variable only. So we go back to our 100 equals 2x plus y and solve that equation for y. And y will be equal to 100 minus 2x. We plug this y equals 100 minus 2x into our area equation so that we can have area in terms of one variable only. A equals x times y becomes A is equal to x times 100 minus 2x. So A will be equal to 100x minus 2x squared. So this is the area in terms of our x variable only. We could call that A of x. We want to find out what is our possible domain. We know that we want our x and y to be positive, so x greater than 0, y greater than 0. And because x and y, the 2x plus y will be equal to 100, then x can be at most 50 if there is no y. So then our constraint is that our x must be between 0 and 50. In order to maximize this area, we take the derivative and we set it equal to 0. A of x will be equal to 100, or a prime x, sorry. A prime of x will be equal to 100 minus 4x by our power rule. Setting this equal to 0, 100 minus 4x equals 0, implies 4x equals 100, and therefore x will be equal to 25. We found x, we want to find y, plug x equals 25 into y is equal to 100 minus 2x, that's y equals 100 minus 2 times 25, so y will be equal to 50. The dimensions here are our length and width. The dimensions to maximize the garden are x equals 25 feet and y equals 50 feet. Now we want to find the maximum area, so use the dimensions at the maximum, multiply them together. So A will be equal to 25 times 50, that's 1,250 feet squared. Let us look at another problem. An open top box is made from a 24-inch by 36-inch piece of cardboard. By removing a square from each corner of the box and folding out the flats on each side, what size square should be cut out of each corner in order to get a box of maximum volume? Let us look at the solution. First step, we want to go ahead and sketch a diagram of what this box might look like. So here's our 36 by 24 box, and if we cut out squares of side length x, 4 squares from each corner, on the length of that box we have 36 minus 2x, because we have an x cut out to the left and an x cut out to the right. On the width side of it we have 24 minus 2x, because we have an x cut out to the top and an x cut out from the bottom. Now if we fold this box up, it will look like a 36 minus 2x by 24 minus 2x by an x, or x is our height. We want to find the maximum volume, so let x be the length of a side of the cutout square. V is equal to the volume of the box. The equation for volume, length times width times height, will be 36 minus 2x times 24 minus 2x times x. Expand this, we get 4x cubed minus 120x squared plus 864x. Our possible domain there, we want our x to be greater than or equal to 0. And considering the shorter side is 24, then our x can at least be, or at most, sorry, be 1/2 of 24. So x is going to be less than or equal to 12. The possible domain, therefore, will be x being between 0 and 12. F of x is a continuous function. I want to take the derivative of it and set it equal to 0 to find the maximum. So v prime of x will be equal to 12x squared minus 240x plus 864. Setting that equal to 0, I have 12x squared minus 240x plus 864 is equal to 0. Simplify it by dividing through everything by 12. We're left with x squared minus 20x plus 72 equals 0. Now let's use the quadratic formula. Remember, the quadratic formula was x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then plug in the numbers. X will be equal to 20 plus or minus the square root of 20 squared minus 4 times 1 times 72 all over 2 times 1. And then our two answers that we'll get will be 10 plus 2 radical 7, or 10 minus 2 radical 7. Note that only one of these is in the possible domain, and this one is 10 minus 2 radical 7, because 10 plus 2 radical 7 is bigger than 12. So the maximum volume, therefore, would be 36 minus 2 times 10 minus 2 radical 7 times 24 minus 2 times 10 minus 2 radical 7, that's times 10 minus 2 radical 7. So our maximum volume would be 1825 inches cubed. Thank you so very much for watching. See you next lesson.